All right, folks. So today we're going to be talking about section 4.3, which includes some rules about multiplication for probability. So before we do that, though, we need to talk about, or we need to have a vocabulary rule, because the reason why it's multiplication rules for probability is that we have two different rules about multiplication depending on the following definition, and that is the idea of independent. So two events are independent if one happening doesn't affect I'll be honest, I don't know whether that's effect or affect. We're just going to roll with it. It doesn't change. Whether the other one happens. Right? So, whether or not I sleep in tomorrow doesn't affect whether I suddenly blanked on any potential possible thing that is reasonable. Let's see. Doesn't affect whether or not the McDonald's down the road has a good day of business, right? On the other hand, whether or not I sleep in tomorrow does have an effect on the probability of certain things in my daily routine happening, right? So two different events can either have no effect on one another, right? One happening doesn't mean the other is going to happen any less or more likely than it would have, or the opposite, right? So one of the things to be very careful with is determining that, right? So especially when you have word problems, figuring out whether two events are independent is one of the probably first things you should do, right? And to that end, there's a key phrase of with or without replacement that comes into play here, right? So we talked a little, or we've talked a lot in these past couple of sections about the sock drawer example, right? And in that case, there's technically been two sorts of stages to the experiment. One was when I drew a white sock, right? It just doesn't have any interesting things to go with it because it was guaranteed to do so. And then one when I drew another sock without replacing that white sock, right? So the fact that the first thing I drew was a white sock actually did change whether I was going to draw a white sock next, right? If I changed that problem up, if we went back to it and said, okay, the first sock that I drew out was a blue sock, what's the probability that the next one is a white sock? That would change all of the work that we did, right? We would get different answers for everything that we worked on there. And if we had set it up in this manner from the very beginning, what I would have needed to be clear about is that it was without replacement, right? And generally when you're doing something without replacement, the two events are not independent. They are dependent, right? That would be the opposite there. If we did draw a white sock and then for whatever reason put it immediately back in the drawer and draw another sock, then those two events would be independent. I would have the exact same probability of drawing a white sock second, no matter what my first sock was, if I put that first sock back in the drawer, right? So another key place this comes up is with cards, right? So I mentioned towards the very beginning that one of the classical examples of probability problems involved drawing cards, but we haven't done any examples like that. And the book hasn't really done any. The book's done a lot more with dice than we have. But the book hasn't done very many card examples because until you get to this stage, card problems are pretty boring. Either you're only drawing one card and there's 1 out of 52 chances and you have some... It's basically just a slightly different die. When we can, or you just have to put the card back and we secretly assume that you're doing it with replacement, right? And that way everything you do is independent and we don't have to worry about this definition yet. But most fun and exciting card draw problems come from when you're drawing cards without replacement, right? When you're playing poker, you're drawing your hand without replacement, right? You're not drawing one card, looking at it, putting it back, shuffling the deck, drawing a second card, looking at it, putting it back, shuffle the deck, right? That's not how you play any version of poker that I've ever heard of, at least. I'm not precisely an expert, but I like to think I would have at least heard of something like that if anybody played it. So card draw problems are usually done without replacement, which means that the events are dependent. They are not independent. They are dependent without replacement. Right? And if you ever have a situation where these phrases can be used and you say with replacement, then those are generally independent scenarios. Right? And so to get to the multiplication rule of all of this, if we are independent, then the probability of E and F happening is the probability of E times the probability of F. Right? And if we are dependent, then, well, first we need to come up with some notation, right? And that's going to be this bar, right? So if I were to read this out loud, I would say this is the probability of F happening given that E happens. Right, so in other words, if we think about it in our past problems, what we were really looking at is the probability that we draw a white sock given that we already drew a white sock. Right? Because we were assuming as part of the problem that somebody already drew a white sock, and we were wondering what the second sock was going to look like. So secretly we were doing that without worrying too much about it because we weren't making it more complicated. And so given that definition, now we say the probability of E and F, let me spell that out to make it more clear. Probability of E and F is, you can write it two ways. You can either say the probability of E times the probability of F given E, or something that's exactly the same, the probability of F times the probability of E given F. Right, and we can shift this around a little bit, right? They have a whole different definition for this, but I don't really see why. Right, if we just want to find the conditional probabilities, right? This thing with the given bar is called a conditional probability. We can just take the formula we have above and divide both sides by the probability of E, and vice versa, right? If we wanted to find E given F, we would just change that bottom E to an F, right? So the other thing that the other sort of multiplication rule that comes out of this is a counting principle, right? So it's along the same lines of what we talked about for our last problem last time with the cats and the dogs, right? Is that a lot of these problems come down to counting outcomes, so we want to have some rules for that. And so the idea here is if your experiment has stages and so stages, let's call it stage 1, stage 2, all the way up to stage N, and each stage has K1, K2, Kn outcomes. Right, so that is to say that stage 1 has K1 outcomes, stage 2 has K2 outcomes, stage N has Kn outcomes. Then your experiment, there we go, has K1 times K2 times all the way up to Kn outcomes. Right, so if you have a multi-stage experiment, then you get the number of outcomes by finding the number of outcomes of all the stages and multiplying them together. Right, so let's do some problems with all these things. So let's do some conditional probability problems. So suppose we have 15 blue markers. 5 of them wide-tipped and 10 fine point, and 10 red markers. 5 of them as well wide-tipped, and 5 fine point. Right, so we're going to find the probability of getting our trial is going to be to pick a marker at random. And so we're going to try to find the probability of getting a fine-tipped given we got a red marker. We're going to find the probability of getting a blue marker given that it's fine-tipped. We're going to find the probability of getting a blue marker given that it's wide-tipped. Oops, I sort of mixed things here, but this is fine point. And then we're going to find the probability of getting a marker that is fine point, and blue. Right? So the trick with figuring out these conditional probabilities is really what happens is this second thing becomes our new sample space. Right? So we want the probability that we get a fine point pen marker, given that we know that our marker is red. So despite having a larger sample space in general, for this one problem, our sample space is our 10 red markers. Because we have the foreknowledge that the marker that we chose is going to be red. Right? We just want to know what's the likelihood that it's fine point. Right? And we have 5 red markers that are fine tipped. So if our sample space, so for this one, our sample space has been restricted to just here. Right? I'm going to bring color back into it because that's the best. Right? Similarly here, we're restricting our sample space to fine point markers. Right? Which means we're restricting to these guys here. Right? And if we look at those, there's 15 fine-tipped markers total. And of those fine-tipped markers, 10 of them are blue. So of our 15 total fine point markers, 10 of them are blue. Right? Now, for this one, our sample space are the wide markers, right? Wide tipped markers. And that means that we're looking at these 10 wide tipped markers. And we want to know then for the top how many of them are blue. So looking at our description, 5 of our blue markers are wide tipped. So 5 of the 10 are going to be the likelihood that if we know it's a wide-tipped marker, 5 of the wide-tipped markers are blue, so 5 out of 10 is what we get for a probability there. Right? So, when we have this and here, right, that means it's not conditional anymore, so we're not restricting our sample space. But we do know that this is, well, we can choose 2 different ways to do it, right? Looking at our formula here. We can either say that this is the probability of getting the blue times the probability of being fine given blue, or this can be the probability of getting a fine-tipped marker times the probability of getting a blue marker given that it's fine. Right? And considering the work we've already done, I kind of like this one better because we already figured out what one of those probabilities is. Right? Either one of these is going to give us the exact same thing, but there's no reason not to use the work we've already done. Right, so, whoops, we know that this is going to be 10 out of 15, right, and so this probability of fine, we need to go back and look at our total number of markers. So, in that case, we're looking at our overall number of markers, which is 25, and we want to know how many of them are fine point, right, so it looks like 15 are fine point. So we get 10 out of 25. Which, in this case, this would have been easy to do because we know that there are exactly 10 fine point blue markers, but this lets us check our work with our formula, right? And the first time you use a formula, it's often a good idea to use it in a context that you can figure out the answer a different way, just to make sure you can check your work that first time you're using the formula. So, let's see. Let's find the probability of drawing a pair of 2s from a standard card deck in 2 draws. Just to be clear, we're not drawing a poker hand. And 1, we want to do it with replacement. And 2, we want to do it without replacement. Right. So for part 1, right, so the probability of drawing a 2 first and a 2 second, right, so that's why it fits in this section, right, we can say it easy enough as drawing a pair of 2s, right, but what that really means is we draw a card and it's 2, then we draw a second card and it's also a 2, right, and with replacement means that it's independent, right? The fact that, well, no matter what we draw on that first draw, if we draw it and then put it back in the deck and then shuffle it and then draw another card, what we got on that first draw doesn't matter, right? So that means that this is the probability of getting a 2 on our first draw times the probability of getting a 2 on our second draw, right? So a standard card deck has 52 cards in it. So our total number of outcomes for either of these is 52, because we could get any card in the deck. And in a standard card, there are 4 2s. So this is going to be 16 divided by 52 squared, which is a big number that if we really wanted to know what it was, we could plug into our calculator. Right? But that's our basic idea there. Right? For the second one, it gets a little bit tricky, right? Without replacement means dependent. Right? So the probability of getting a 2 first and a 2 second is going to be either the probability of getting a 2 first and then, I always have to look it up. There we go. Probability of getting a 2 second given you got a 2 first. Or it can be the probability of getting a 2 second times the probability of getting a 2 first given you got a 2 second. Now, either of these are technically fine from a math standpoint, but the first one is the only one that makes sense from a word problem perspective, right? Or at least in terms of figuring it out, right? Because this one says we need to find the probability of getting a certain card second, given that we already know what our first draw was, right? Whereas this one says we need to know the probability of getting a certain card in our first draw, given that we already know what the second one is, right? It makes a lot more sense that we drew a card, looked at it, know what it is, and then draw our second card, right? Either way, it doesn't make too much difference, because the probability of getting a 2 on our first draw, right? So if we go ahead and go with that one, right, that's going to be a 4 out of 52 again, right? There's 52 cards in the deck. We draw one, and then there are 4 different possibilities for that too, right? And so for this given one, right? If we already know that our first draw was a 2 and we didn't put it back in the deck, right, then we know that we're drawing from 51 cards. And if we already know that that first card was a 2, we know there are only 3 2s left in the deck, right? So that's why this bottom one doesn't make much sense, because it's a lot harder to figure out the probability of getting a 2 second if you don't know what your first card was already, right? The fact that we know in this one right here, we know that our first card was a 2, right? Which means that we not only know that there are 51 cards in the deck left, but there are 3 2s left in the deck, right? If we did this guy here and we don't know what our first card is, we don't actually have any tools to do that yet, right? So you're always going to want to use this one when you're dealing with card draws, just because it's the one that makes sense, right? So this is 12 times 52, 12 over 52 times 51. Again, that's something we could plug into our calculator if we cared what the actual numbers were. But that's how we figure out probabilities with replacement. Right? So going to counting principles. Right? So we could ask a question like, how many 6-digit pens, and I mean pens like capital, are available in hexadecimal, i.e. 0 through 9 and A through F are allowed, right, as digits, right? So what that means is that we have 6 different stages, right? Digit 1, digit 2, digit 3, 4, 5, 6. Right, so those are our stages, and we just need to know how many different possibilities, how many outcomes are there for each stage, right? If we choose a digit at random, how many different choices we can make? Well, 0 through 9 gets us 10, A is 11, B is 12, C is 13, D is 14, E is 15, and F is 16. So we get 16 to the 6th, which is again, really big number that we could plug into our calculator if we wanted to know what it looked like exactly. And so maybe we change it. What if we aren't allowed any doubles? Right? So each digit has to be distinct. None of them are allowed to be what any of the digits before are. Right? So again, we have our 6 stages. And if we're not allowed any doubles, well, our first digit can be whatever it wants, right? There are 16 possibilities, so that digit can be whatever it wants. But now, when we're randomly choosing for stage 2 here, right, we're not allowed to have any doubles. We're not allowed to be any digit we've been before. So there are only 14 choices for us to make. 15 choices for us to make, right? Because we had 16 to start with, but now whatever random one we chose here, we're not allowed to choose it again, right? Similarly, when we go into stage 3, we've already chosen 2 digits that we're not allowed to choose anymore ever again, right? So the number of possibilities is 14, right? And similarly, we get 13, 12, 11. And again, that multiplies to be a really big number that we really just need a calculator to tell us what it is. All right. So we don't just want to use this for counting things. We'd like to use it for probability. So in Clue, there are 6 suspects, 9 weapons, and 9 rooms to choose from. What is the probability of getting at least the weapon and the room correct? Right. So we need to count 2 things, right? This is a probability question. So we need to know the number of things in the event, and we need to know the number of things in the sample space. Right? So the number of things in the sample space are the total number of guesses. Right? So if we want to know the number of things, there's 3 stages. Right? There's guessing the suspect, the weapon, and the room. And there's 6 different possibilities here, 9 different possibilities here, and 9 different possibilities here. I think we get that, if I did my quick math correctly. So the number in the event, right, we can think about that as having the exact same 3 stages, but the number of possibilities have gone down, right? So if we want to get the weapon and the room correct, then there's only one option for each of those, right? Oh, there only one weapon did it, and it was only done in one room. It's generally pretty hard to kill someone in 2 different rooms, right? It's more possible to do it with 2 different weapons, but in the game of Clue, there's one weapon in one room, right? But we don't care, at least in this question, about getting the suspect right, so we still have 6 choices there. Right? So the probability of E is going to be 6 divided by 486, which is 1 in 81. Right? So that's how we can use the counting principle to help us do probability stuff. So next up is chapter 5, and the idea for that is that sometimes probability is a little bit harder than classical probability can handle. Or at least not necessarily harder, just more complicated. So that's what chapter 5 is all about, is getting us some tools for some more complicated ideas than classical probability can handle all on its own. So that's what we'll be talking about next time. And I will see y'all then.